Hi everybody, welcome to another video. I'm just going to respond to those comments on the Google Classroom about which topics you'd like me to cover over the next video or two. So what I'll do is I'll put some links in the description to the timestamps and everything so you can see what the topics were and try and put some questions at the end as well for you to practice. Okay, so the first topic that we have is harder probabilities. So I'm assuming you mean those sort of questions where you have unknown numbers of things in a bag or something like that, where you have to generate a quadratic equation out of that and solve it. So if we have something like a bag containing 5 reds and some greens, but we don't know how many greens that we have, but we know that the probability of picking 2 greens is some number like 7 out of 22. Okay, so they want to know how many green or how many there are in total in the bag or something like that at the end. So we just have to make sure that we answer that at the end. So a quick probability tree always helps us here. We can go red, red, or we can go red, green, and then we can go green, red, and green, green. So the probability of going green, then green is 7 out of 22. So the probability of the first green multiplied by the second green is 7 out of 22. So they're actually giving us that information, but we don't know what the number of greens are. So we represent that algebraically with something like, we call the total number, let's call the total number x. So the number of greens is going to be x minus 5, because there's 5 reds, the rest will be greens. Let's say there were 20 in total. That means there would be 5 reds, there would be 20 minus 5 greens. Out of the total, which is x, so that's this probability here of getting the first green. Then we multiply that by the second green. Now, if these were numbers, let's say it was 20 in total. The first one would be 15 out of 20 for the greens. And then we would subtract 1 and have 14 out of 19 for the second greens. Okay, so we don't know what these numbers are at the moment, but we know that the next one will be 1 less for the greens. So x minus 5 minus 1 would be x minus 6. And the total here, instead of being 20, would be now 19, so that'd be x minus 1. So sometimes putting some numbers in there to help, we'll see what the algebra is. And when we multiply those together, we are told that that will give us 7 out of 22. Okay, so we can now use this equation here to solve with some algebra, and then that will give us our value for x, which is the total. So we have x minus 5 brackets x minus 6 over x brackets x minus 1, and that equals 7 over 22. So we can cross multiply these and expand out. I'm just going to expand the top first, so we'll have x squared minus 6x minus 5x, and then minus 5 times minus 6 is plus 30 over x brackets x minus 1, and that equals 7 over 22. So this is where we can cross multiply. I'm going to multiply both sides by 22, so I'm going to put a 22 there, which will get rid of that, and I'll multiply both sides by x brackets x minus 1 to get rid of that. Okay, so hopefully you can see that the cross multiplying happening there. So we've got 22x squared minus 22 times, this will become minus 6x times minus 5x is minus 11x. So 22 times 11 is 242, I think, plus 30 lots of 22. Let's have a look at the 30 times 22. Is that 660? Yeah, plus 660 equals, and on the right side we've got 7x times x and 7x times negative 1. Okay, So we can rearrange this to get 15x squared. If I take 7x squared from both sides, and I'm going to add 7x to both sides to get minus 235x plus 660 equals 0. So that's the final quadratic equation when we've rearranged these. So we can now go to our quadratic function, 15 minus 235 and 660. And we get the first x value is 12, and the next one will be 11 over 3. So x equals 12 or 11 over 3. Okay, so if you need to, you can put that back into brackets, or I would use the quadratic formula there, minus b plus or minus, etc. That's in the front, and then that will give you your two x values. And we're going to ignore the fraction because we can't have a fraction of whatever these were, red counters or sweets or whatever. So we now know that x equals 12. That's the total number of things in the bag, and if it wants us to find the greens, then we would just take away 5. X take away 5 is the greens. So 12 take away 5, that's 7 green counters. Okay, so if you want to practice these for yourself, then what you can do is just choose random values, like reds equals, let's say 10, green equals, let's say 15, but you're going to make that the unknown one. You can put whatever values you like in here. Okay, and how I sort of created this question is that I just said, right, if I go green and then green, that would have been 15 out of 25 times 14 out of 24, and you can work that out on the calculator. So 15 over 25 times 14 over 24, 7/20. So what you can do is you can pretend that the question is, when you take green and green, the probability is 7/20, and then you can work backwards. Okay, so pretend that you didn't know this, you didn't know this, you didn't know this. The 15 is the total minus 10. So the first one would be x minus 10 over the total, multiplied by the next one, we take one off, x minus 11 over x minus 1 equals 7 over 20. Okay, and see if you can create your own question and see if you can get a rearrangement of that which will give you 25 for x. And then you could take away the 10 and get 15 for the greens. That's how I did that question. That's how I made it up before the video. So that's all you have to do if you want to practice that kind of question. And you can mix it up. You could do red, green, green, red, and you could say the probability of getting one red and one green, and you could work this out. So it'd be 10 over 25 times 15 over 24, and then this one would be 15 over 25 times 10 over 24, and you multiply those two together, add them together, and get your probability here to start with. And that's another type of question that they ask. So when you're doing these harder probabilities, you're trying to generate an algebraic equation from the information that they're giving you. Just make x the total, and then the greens would just be x minus the number of reds, for example. Okay, hopefully that helps with the harder probability. If you're talking about the ones with the counters or anything like that, you just have to simplify it down to evens and odds if you can, or just work out all the different probabilities and add them together. The next topic is simultaneous equations. So if we have a look at simultaneous equations, starting from the beginning, simultaneous equations is all about finding on a graph the two graphs that we have, let's say this one and this one. We're finding out the intersection coordinates, x, y. That is the x coordinate here, so that's x, and that's the y coordinate of where the two graphs intersect. Okay, so if you have two equations, two unknowns, usually x and y, but not always, sometimes it's a and d, like from the sequences, but essentially you have to solve them simultaneously, and there's two ways of doing that. So if we have 2x plus 3y equals 5 and x plus y equals 2, then we can double the second equation, or we can triple the second equation, or we can rearrange and substitute into the first equation. So we can use substitution on these, but usually you would have fractions in there and it makes it difficult, so you just multiply them out. So y equals 2 minus x, we can actually substitute that into the first equation and replace the y with 2 minus x and solve that. So 2x plus 6 minus 3x equals 5. Rearrange that and we get x equals 6 minus 5 is 1. So y equals 2 minus x. 2 minus 1 is also 1. So the solution to this would be x comma y is 1 comma 1. So when you have two linear equations like that, you can either double them, triple them, whatever you need to do to get them the same, and then you subtract them, or you add them depending on the signs. But remember, we have our menu. You go down to equation function, and simultaneous equation, number of unknowns for GCSE will always be 2, and then I can just put in the 2x, the 3y, and the 5, 1x, 1y, and 2. That gives x equals 1, y equals 1. So make sure you use your calculators to help you out for the linear ones. When we have one linear and one quadratic, that's when we would have a quadratic equation looking like that, and then maybe a straight line going through them. And what you'll find is you get two solutions to this where they cross over. This one here, x1, y1, and x2, y2 here. Two separate values for x and y. So if we have an equation, let's just do x plus y equals 7, and what did I have? X squared plus 2y squared equals 33. Okay, so what we have here is a linear term, a linear equation here, x plus y equals 7, and a quadratic here with the squares in. So we're going to rearrange this first equation and put it into the second equation, just like we did here, substitution. Which one do we choose? Well, in this case, it's actually probably easier to substitute for x, because we've got the 2y squared there. So if we had y equals 7 minus x, we just have the double brackets, and then we'd have to times everything by 2, which isn't too big a deal, but this one is probably slightly easier. So we're going to substitute for x, and then multiply that out. So 49 minus 7y minus another 7y plus y squared. Plus 2y squared equals 33. And then we're going to collect these together. So we've got 49 minus 14y plus y squared plus another 2. That's 3y squared. And I'm going to subtract 33 from both sides to try and get 0 on the right. 3y squared minus 14y, 49 minus 33 is 16 equals 0. So menu A22, you might use a quadratic formula in the exam to just do this, or once you get your brackets, if they're kind of easy. So we've got 8/3 and 2. So we know that one of them's x minus 2 because it gave a value of 2 there, so the bracket's the opposite. So we know we need a 3, oh sorry, these are y's. We need a 3y and we need a negative 8 to get the positive 16 like that. So that will give us y equals 2 and y equals 8/3. And then to find x, we do 7 minus y, so 7 minus 2, 5. And then, x equals 7 minus 8/3, 13/3. Alright, so this is how you do them. If you ever see a question that's got the words intersection, that's probably going to be simultaneous equations. Okay? If you see anything crossing over, like you actually see it on a graph and it says solve these simultaneously, then you're looking for the point of intersection of those two graphs. Okay? Anything at its highest level, okay, these quadratics are usually circle equations. Okay, you don't have to know about circle equations, but that's what these x squared plus y squared look like. And we usually get one going through and we get our 2 points here. Okay, I have seen on maybe one paper where when you solve this, it gives you one solution that's repeated. Like if you had a quadratic equation that had x squared plus 2x plus 1 equals 0, okay, and you solved that and you got x plus 1 squared. So x equals -1 twice. Okay, if you ever get that situation where the quadratic gives you just one solution, that means that this blue line is a tangent to this circle. So in this case, we'd look for the x value here, and it's twice because it actually intersects twice on the curve, and the y value is there's just one y value there, one x value. Okay, this is kind of bordering on A level here, but this is a rare situation that's happened once in one of the old GCSEs. So just bear in mind that's one of those situations there. Okay, functions. For functions, they nearly always go in the same format. They'll give you a function like f of x equals 2 over x plus 1, and they'll say for question A, which value of x has to be excluded from the domain. Okay, all that means is we have to look at a value of x which will give us an error on our calculator. Okay, and the main one is when we divide by 0. We're not allowed to divide by 0, so our denominator cannot be equal to 0. So we have to solve an equation where x plus 1 in this case is equal to 0, so x equals -1. And if I put -1 into this, then I will get 0 on the denominator, and I can't do that. I can't have that. So x equals -1 will be the value excluded from the domain. Okay, if it was 2 over x, then x equals 0 would be the equation that I solve. It's done straight away for me, so I couldn't have x equals 0. Okay, if it was 2x minus 3 on the denominator, something 3 over 2x minus 3, I put 2x minus 3 equals 0, 2x equals 3, x equals 3 divided by 2, or 1.5. So I couldn't have 1.5 on my graph. A bit of background on this is when you have an equation like 1 over x, it looks like this. You should know that one. Y equals 1 over x. When x equals 0, which is this vertical y-axis, okay, you'll notice that there's no points on this. This goes straight up, 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 but never touches this. This one goes down, 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 and never touches down there. Okay, and the reason for that is because when x equals 0, 1 divided by 0 is, well, it's undefined, but it's going up towards infinity, but never actually touches. If you choose any other value for x on here, like 2 or 3 or 4, there'll be a corresponding y value, but not 0. Okay, then we have something like g of x equals, I don't know, 4x plus 2, and it says find fgx, like that, fg of x. So we take g of x, which is 4x plus 2, and we put it into f. So we do f of gx, which is 4x plus 2. And we just replace the x here, so 2 over something plus 1, we're replacing that x with the 4x plus 2. So there's the x there from the f of x, and we're replacing that with the 4x plus 2. And we simplify that to get 2 over 4x plus 3. So that's what's going on there with these compound functions. We take the one that's closest to the x first, and then we put it into the one that's further from the x. What they also get you to do is to do the inverse of this. So find the inverse of g, and we're going to call that y. So we'll do y equals 4x plus 2, and then we replace the x and the y's, we switch them round, so x and the y's in all cases. So if I had, let's say I had y equals x over 2x plus 1, that would become x equals y over 2y plus 1. That's where a few of us made some mistakes on the last mock. Okay, so we make y the subject, take 2 from both sides, and then divide by 4. So we get y equals x minus 2 over 4. And that is our inverse function. Okay, and what does it mean to be an inverse function? Well, if I just do another layer here, if I have a graph like this, and my original function is something like that, then when I do my inverse, I'm reflecting this on the line y equals x. Okay, so that means, let's say this point here is 0, 4, then the x becomes the y and the y becomes the x. So that would become 4, 0. That point there would become that point there. And this point here, this might be minus 1, 0. Then that would become 0, minus 1 down here. And you can see that as I draw this line, it's a reflection in the line y equals x, because all of the x coordinates become the y coordinates of the other one and vice versa. So that's why we replace the y and the x and then solve it. The only thing we have to worry about, let's say we have hx equals 2x squared plus 6x plus 3. Okay, if it ever asks us to do the inverse function of a quadratic, okay, we can't just replace the x and the x here with the y's. We have to complete the square first. Okay, so we have to then take the the 2 out as a factor, and then complete the square on that. So x plus 1.5 squared minus 1.5 squared, and then plus 1.5, like that. So once we've done this thing, we've got x plus 1.5 squared minus 1.5, so 1.5 squared, take the minus of that, and then add 1.5, minus 3/4. So our final thing here is 2 brackets x plus 1.5 squared, and then minus 3/4 times 2 is minus 3/2. Okay, so now that we've completed the square on this, we can actually do the inverse. So we make y equals that, and then we switch the x's and the y's around from the completed square. So y plus 1.5 squared minus 3 over 2, add 3 over 2 to both sides, and then divide by 2. That gives me y plus 1.5 squared. So I square root both sides, get plus minus, and then I subtract 1.5 from both sides, and that will give me my y equals. So that will be my inverse function there of this quadratic. Okay, so a little bit strange there, but hopefully you can see what's going on there in terms of the quadratic, when you have to take the inverse, we have to complete the square first. Okay. Next one was shading inequalities. So if we have a graph of y is less than or equal to 3x plus 2, like that. So this would go through at 2, and when y equals 0, then we've got negative 2 equals 3x. When I rearrange this, x equals minus 2/3. So that point there is minus 2/3. So to shade this, what we're looking at is, if we're on the line, if we're on that line there, then for every value of x, we get the exact value for y. So let's choose this point here, x equals 4. Then y would be equal to 3x. 3 times 4 is 12, plus 2 is 14, so not to scale, but this is 14 here. Okay. If I was to choose a y value less than 14, like 13, or 12, or 11, or 10, or anything like that, it would be, for that corresponding value of x, it would be any of those y values that are less than or equal to 14. So 13, 12, anything in there for that value of x. Okay, if we choose another value of x, let's say x equals 1, then 3x plus 2 is 5, so that would be 5. A y value less than 5 would be 4, 3, 2, 1, like that. So hopefully you can see that when y is less than or equal to, that's the areas underneath this graph, and it's same for the negative, like that. If I was to choose a y value that was greater than that, then I'm just looking for the ones that are above the line. And that's how we do these questions. We start to build these up. Okay. If I have my graph and it says x is greater than or equal to 3, x is equal to 3 is there. Our line x equals 3 is this one here. And if I wanted to choose any x value that was bigger than 3, like 4, 5, 6, it would be these ones. Okay, and because it's greater than or equal to, I'd actually make that a solid line. Okay, so in this case, the arrow, the greater than sign, is pointing in the direction of where you shade. Okay, so to the right of the line. If we do y is greater than negative 2, let's plot the line. There's negative 2, so we do a dashed line for this, because it's just greater than and not greater than or equal to. And I want a y value that's more than negative 2, like minus 1, 0, then the y values would be these ones. Okay, so all we have to do for these shaded inequalities is to think y is greater than negative 2. So y minus 1 would be that line there, 0 would be there, 1 would be there, 2 would be there. So all of these are the ones that we're looking for, and they'll build these up and maybe have like 2 or 3 of them, and you have to decide where these shaded regions are. So let's put all these together. Can I do that with this? No, let's just make another one. So if we put all these together, and we have y is less than or equal to 3x plus 2, y is greater than negative 2, and x is greater than or equal to 3. They're the 3 that we had. So we'll put our line in, and y is greater than negative 2 was that one, negative 2, and 3 for the x would be there. X is greater than or equal to 3, y is greater than negative 2. So let's think about this then. Let's do the first one in red. It's less than, so it's all of that region there. Then we've got to be greater than negative 2, so we've got to be above this line. and then we've got to be to the right of 3. So we've got to be this side of 3. It starts to look a bit messy, so let's try to think about that. We've got to be underneath this line, to the right of this line, and above this line. So we're looking at this region here. Okay, underneath the diagonal line, to the right of the vertical line, and above this horizontal line. This is the x and y axis, x-axis and y-axis. This is -2. So in theory that would be a dashed line like that. Okay, and that's how we build up those inequalities. Okay, transforming graphs. So if we have a look at transforming graphs, then I think we'll just go through the different possibilities of transforming. So if you think about it, all we can do to a graph is we can move it up and down, we can move it left and right, we can squash or squish up and down, or we can squash or stretch up and down, or we can squash and stretch left and right. Okay, so there's 8 different things that we can do there. So let's have a look at y equals f of x is our standard graph. If anything is outside of the brackets, that will affect the y. So outside of the brackets affects the y, and inside of the brackets affects the x. Okay, so let's look at the different things that we can do. We can put a number, let's say a. We can put a number outside the brackets, plus or minus, and that's going to shift this graph up and down. So plus or minus a outside of the brackets is going to move it up and down. If we have a number, let's say b, in front of the f of x, so outside of these brackets, then it's still affecting the y. That's going to stretch the graph by a factor of b. So if we have y equals f of x, and then we have y equals 3f of x, then everything on the y side will be stretched by a factor of 3, so a multiplier of 3. So let's see if we've got, let's just do a strange looking graph here, and this point here is 3, 2. Okay, if this is y equals f of x, then 3f of x, then this y coordinate here will be stretched by a factor of 3, so that would go up to 6 up there, 3, 6. This one here at 0 will stay there because 0 times 3. This one would be 3 times bigger, so that one there, let's say that that's 0, 4. That would go to 0, 12, so that would be up there, and you can see the whole thing is stretched by a scale factor of 3, because the 3 is outside the brackets, and that's going to affect the y. If we do something inside the brackets, it basically does the opposite of what happens on the outside. Okay, so if we do plus c here, so plus c, like adding, outside of the bracket, shifted it in the positive direction. Okay, but inside the brackets, it's going to shift it to the negative direction. Okay, the negative of that plus c. So you would think that plus c would shift it that way. Okay, but it doesn't. The plus, all right, let's put it on this one here. Plus c, you think it would go that way, but it's the opposite of what you think. So plus c would go that way, and minus c would shift it that way. Plus a would go upwards, and minus a would go downwards. So this is plus or minus c inside the brackets. So this affects the x, so it's shifting it left and right, but it's the opposite to what you think. Okay, similarly, if I put a number in front of the x and make it a multiply like d, so dx, like 2x, f of 2x, outside of the bracket that would have been a stretch in the y direction, but inside the brackets it does the opposite, so it's a squash. So when we have dx, that's going to squash by a factor of d, multiplied by d. Okay, so inside the brackets affects the x, so it's being squash in the x direction by a scale factor of d. Okay. Other things to note, if I want to squash in the y direction, then this b would be a fraction, such as a half. So if you have sine of a half, it's going to squash it. A half sine x, half sine x would be a squash that direction because there's a half in front of the function. If I have f of a half x, then it's inside the bracket, so it's going to affect the x, and it's multiplying, so it's going to be a squash, but it's a half. Okay, so it's doing the opposite of what you think. You think a half's going to go half as big, but a half would actually go outwards like a stretch. Okay, so they're doing the opposite of what you think they're going to do inside the brackets. Okay, now if you want to practice these, you can go to bowtieteacher.com, and the level 8, I think it is, has some coordinates. It will just give you a coordinate like, I don't know, 1,4, and it will say, well, what will happen to this if this is the original f of x? What will happen if I do f of half x? Okay, where will that new coordinate be? So if we think about it, the half x is inside the x brackets and it's multiplying, so multiplying by a half, it's going to do the opposite of what you think. It's going to make it bigger by half in that direction, so it's going to be at 2,4. Okay, if it was f of 2x, then the 2x, if it was outside the brackets, it would stretch it by 2, but inside the brackets it will squash it by 2. So that 1 will be coming squashed closer to the y-axis, so that bit is squashed by a factor of 2, so that will become 0.5,4. Notice that the y value is not affected by this. Okay, in the exam they might do combinations of these things, so you might have like y equals 2 f of x minus 3, and it will say what happens to that graph. So we've got the minus 3 outside and the 2 is outside, so this is only going to be affecting the y values. Minus 3 is going to be a translation 3 units downwards, and then once you've done that, you're going to stretch it by a scale factor of 2, so stretching the y by a factor of 2. You can do them either way around, that will still work. Okay, so try the website and see if you can master all of those. We haven't talked about the negative signs. If there's a negative sign in front of the b, like that, minus b, like minus 2 f of x, then that reflects in the x-axis. So all the y's will become their negative of each other. If you choose a y coordinate, it will become its negative. And if it's f of minus x, then it reflects in the y-axis. Okay, so all of the x values will become its negative. The y values will still stay the same. Okay, right, moving on, we've got some circle theory stuff. So I've got GeoGebra open here, and we have a tangent, and we have a circle, and a couple of chords. So remember, a chord is a line that cuts the circle at 2 points here and here, C and B. And what that does is it splits the circle. This is the important point that maybe some of you don't quite fully get, is that when you have a chord like BC, that splits the circle into 2 chunks, 2 segments. Okay, the bigger segment, which is going from here around, is the major segment, and the smaller chunk, CB, and then this bit down here is the minor segment because it's smaller. Okay, and we use these terms segment in two of the circle theorems, I think. The one with the bow tie, where it goes like in the diagonals, and we say that they're in the same segment. So let's just look at that in a bit more detail. Let's do let's create some points and do some segments. So this is the minus segment BC, and then this lower bit down here. So if I create this form here, okay, hopefully you can see that D and Q, they're in the same segment. See that? Those two angles there and there are in the same segment. And these two, P and R, they're in the other segment, okay, or alternate segment you might call it. And let me just drag these points, and you can see that if I move them, the angle doesn't change. They're exactly the same. Okay, so we say that angles in the same segment are equal. D here, it doesn't change the angle. See that? Okay, and if I put the, well, you can see the angles in there, they're not changing. Okay, so we can prove that by showing these points on the circle. Okay, but I think most of you understand the whole bow tie thing, but the one that's difficult is the alternate segment theorem when we've got this chord here. That means if I make any other angle in the major segment, okay, because we've got an angle, let's say an angle down here, let's say that angle there is 46 degrees. Let's just make that a bit clearer there, 46. Hopefully you can see that that angle is in this minor segment down here. So I can create an angle in the major segment anywhere, and that will still be the same. Okay, because, oh, sorry, we don't want that one. Let's create a segment. We're going to do there to there. So I've just created an angle D, which is in the opposite segment to this one down here. All right, so let's just double check that angle there. 46.69. It's the exact same angle as this one down here. Okay, so I can move this anywhere because it's in the alternate or the other segment to CBE, that angle 46.69 down there. This is anywhere in the other segment. Okay, if we do the same thing for the other side, let's make the angle down here. No, we don't want that one. 65 degrees. Okay, that means that we've created an angle in like DBF, that's the minor segment now. Okay, and this circle here, this big segment here, this big chunk, is the major segment. So that means if I move this one here, that's also going to equal 46.71. So 46.71 there. Okay, so that's what we mean by alternate segment, is if we create an angle in one segment, then the one in the opposite one will be the same. Okay, hopefully that kind of makes that clear. And the final thing we had was intersecting chords theory. So I've got another one here, which hopefully you can see I've got these lines crossing through the circle. So there's chords there, and what we're doing is we're looking at I to M. M is the sort of intersection point there. IM, that's 6.04 times 5.47 is equal to KM times OM. All right, so if you do those, let's make it a little bit different like that. So IM, so from the point I to the middle, or where they intersect, is 7.11 times NM is 4.16. That gives you 29.57, and 7.27 down the bottom left times 4.06 is 29.5 as well. So those 2 points, I to m times m to n, is equal to k to m times m to o. Alright, hopefully you can see that. Now, if I take these points outside of the circle like this, okay, so you can see that I've just taken the circle and I've taken this outside. I've got the same points, but the formula is slightly different now. Okay, now we have I to m is the whole distance from I to the point where they cross over, and then I have n to m is the bit outside the circle. So I to m times m to n is equal to k to m times o to m. Okay, so all I've done is just moved them outside, and you can see that it's the same formula. It's just it looks slightly different, but that has now gone on the outside. So the formula changes slightly. It's not in times nm, it's I to m. The whole of that length there multiplied together will give you the same thing. Okay, so hopefully that demonstration there has helped you with your intersecting chord theorem. If you have any doubt about those, then you can use GeoGebra if you want, or actually just draw it on a piece of paper and measure them and see if they give you the same values when you multiply them together. Just that act will probably cement that into your memory a little bit more. Okay, hopefully that's been useful to you guys. If you have any more topics that you'd like me to go through, then I'll try and do that for you. Just message me or leave a comment on the Google Classroom and I'll make you a video. Okay, good luck.